Okay, now I'm going to talk about weak acids and how they behave quite a bit differently than strong acids. I'll eventually do weak bases as well. But this is just an example of a weak acid. I use HA, where H indicates the hydrogen ion, A would indicate the anion. So as an example, I might use acetic acid, H, C2, H3O2. And so why I use HA is to make, just to shorten things up. So this would ionize out into the hydrogen ion and then the acetate ion, C2H3O2 negative. Okay, so this is my weak acid. The weak acid, in fact, reacts with water, or again, we can just show it by ionizing one hydrogen ion, and it turns into the hydrogen ion or the hydronium ion and that one acetate ion. So here I show it two different ways again. So a weak acid never fully dissociates. So there's some degree of dissociation, but not all of it. So it's actually an equilibrium reaction. It progresses toward the right and it also progresses back to the left. There's a continuous shift from product to reactant. And so we set up an equilibrium expression, just like chapter 15, and it looks like this. It's the hydronium ion and the acetate ion over the molecular form of the acid. Again, I can just express it with just the hydrogen rather than the hydronium. So this is an equilibrium, and that's an equilibrium constant. We call it the acid dissociation constant, but it's the exact same thing as the equilibrium constants in our last chapter. So let's say we want to calculate the pH, calculate the Ka given pH. So if I have a 0.1 molar solution of an acid, formic acid, again, an organic acid, weak acid, that has a pH of 2.38, and I'm asking you to calculate the Ka. Well, here's how it would ionize. Just the simpler form with just the hydrogen ion rather than showing the hydronium. And so I set up my equilibrium expression, and my equilibrium expression is the two products over the reactant. And let's say that I'm going to try to calculate this Ka value. I have it written here, but that's my answer that I will eventually get to. So if I want to find the value of the hydrogen ion and the formate ion, I have to take my pH value, which is 2.38, and do an inverse calculation of the pH. So the formula that I use is down here. I take my pH and I'm going to plug it into this formula to solve for my hydrogen ion, because in my expression I know this value is 0.1. That's the given molarity of my weak acid. But I somehow need to figure out what this value is and what this value is. I can do that from the pH. I know because of the 1-to-1 ratio here that they're going to be the same value. So I take my pH and I'm going to plug it into this equation down here. I'm going to take the inverse log of negative pH. So it's just taking the opposite. You're doing the opposite of what you would do to find the hydrogen ion. So I plug in, I hit the shift log or negative log, and I'll get the value for the hydrogen ion concentration. So what I get is that at equilibrium, my hydrogen ion concentration and my formate ion concentration are 4.2 times 10 to the negative third. Now I know that initially I'm going to start out with this amount of my formic acid, the HCOOH. And so at equilibrium, it's going to be 0.1 minus the amount that this side went up by. And so what I see is that this value of 4.2 times 10 to the negative third is very small. So I can say that at equilibrium, I'm going to ignore that amount, and I'm going to call the equilibrium amount of the formic acid the same as it was originally. It just makes your calculations a little bit easier. I'm going to talk about when you would have to consider that minus part as we move forward. So if you now take your values that we calculate here, my 4.2, so it would look like this, 4.2 times 10 to the negative third times 4.2 times 10 to the negative third on top. All right, so I'm really just taking these values of x and I'm plugging into this equation here. And then I'm going to divide by the formic acid concentration. And so that value will give me my 1.8 times 10 to the negative 4. Now, I'm going to look at what do I mean by percent ionization. So percent ionization is really pretty easy. It's really just how much hydrogen ion you have at equilibrium divided by your initial amount of the molecular form of the acid times 100. That's all it means. The percent ionization for a weak acid is going to be very low. Okay, now, how would we use Ka to calculate pH? So now we're just doing backwards of what we did in the previous example. So let's say I have a 0.3 molar solution of acetic acid. It's going to ionize with the double arrows. If you're being asked to calculate Ka, you know you're dealing with a weak acid. That's the easiest way to determine the difference between the weak acid and strong acid. Your questions related to Ka are going to deal with weak acids. So if I have my solution of acetic acid at 0.3 molar, I'd set it up like this. If I know my Ka for the acetic acid is 1.8 times 10 to the negative fifth, that would be a given value in the problem. Then I know that the Ka expression is going to be x times x. Those would be your two products divided by the equilibrium amount of the molecular form of the acid. And we're going to say minus x. But we're going to ignore that x. For now, I'm going to tell you to just always ignore that amount x, because that amount x is the amount this goes down by, which is equal to the amount that this goes up by. And that's what we saw in the ice chart on the previous page. So then if I do some algebra, I solve for x, I get 2.3 times 10 to the negative third. I know that the x is my hydrogen ion. I then plug into my pH equation. I get my pH. So what can we do for the ionization? Let's look at how to solve for percent ionization of this weak acid. So I find out the equilibrium amount of the hydrogen ion. I take the original initial amount of the weak acid, I multiply by 100, and it's 0.77% ionized. That's very small. That's not very much. So there's that percent ionization equation. I'm going to stop